Today we discuss two small topics. One is solenoid, other is toroid. Okay. So basic the concept of application of actually the Ampere's law here. If you know that what is Ampere's law and how to apply the Ampere's formula, that's the very easy to concept here. One is solenoid, other is a toroid. Solenoid. Here there is a dot. Okay, there is a dot, 2, 3 and 4 dot. There is a 4 cross. Okay, so a wire connections look like this. Now the current direction dot means is towards me. Current direction towards me and cross and towards the board. So current directions look like this. Okay, and behind that, suppose it look like this. If I stretch a spring, okay, stretch a spring, it's look like a, if I stretch the spring, so this is look like that. Okay, and that's the current direction I. Okay, now if there is a current direction I, so there is a magnetic field. So here is the magnetic field. So right hand thumb rule. So the current, thumb represent current and other forefinger, curl of other forefinger represent a magnetic field. So here is the magnetic field, circle. Okay, so magnetic field that is look like this. Okay, so anti-clockwise direction. That's the magnetic field B. Similar here. Similar here, third point. That's the magnetic field B. That's the anti-clockwise direction. Here same magnetic field, but it cross. So that's the clockwise direction. The magnetic field here is a clockwise direction. Similar here. Here also. Okay. Oh, sorry. That's a downward, upward, that's a downward. Okay, that's the magnetic field B. And here, now at that point here, its magnetic field is look like this. Okay, in that case. Similar case here, small stretch here. Here, now almost look like a straight path. Similar case here. So magnetic field is a vector field. Okay, remember that. Magnetic field is a vector field. So at that point, like here, say both magnetic field are in opposite direction. You see that here is a magnetic field in that direction, here in that direction. So at this point here is a no magnetic field. Okay. So that's why this green color line passes. Now there is a straight line here. Okay. Now that's the current direction I, Clear? That's a solenoid. Okay, stress a spring. Okay, that's a solenoid. Now, is here the important point. Suppose here is a point P point here. Suppose as I choose a point P. Now, what is the magnetic field at point P? The important question. Now, you check that this green color actually line is joined here. Now, this line is far behind, joined here. Similar down here. Right here. Okay. So, here is in that direction. Okay, so what is the magnetic field at point P? And you see that there is an opposite direction of magnetic field. Okay, there is that to opposite direction of magnetic field. That's why the total magnetic field that outside of the solenoid be the zero. So magnetic field at point P be the zero, because the direction you see that very carefully. Okay, okay, see that there is a bottom line. There is a bottom line in that direction and top line in that direction. So if I combine these two, so total magnetic field is zero. So outside the solenoid, in case of ideal solenoid, so outside the magnetic field is zero. But practically there is some magnetic field present here. Okay. Now we consider there is the ideal solenoid. So outside the solenoid, magnetic field will be zero here. Outside of solenoid, magnetic field be zero. Okay, here also, if I choose a P dash point here, same condition. Here is the magnetic field in that direction, right to left, but here that is the opposite direction, left to right. So that's why the magnetic field be the zero here. Okay, that's important. The magnetic field created by the current actually. Okay, now there is a strong helical loop. This is a strong helical loop, and inside a magnetic field. But here the important key point: inside there is a fixed direction of magnetic field. If someone choose the point P double dash here, there is a magnetic field. But outside the solenoid, there is a no magnetic field here. Okay. Now you choose any Amperian loop here. Suppose you choose an Amperian loop. Suppose these are the Amperian loop here. Like you choose a Amperian loop. This is a closed Amperian loop. Okay, and now this look like direction is this. This is the anti-clockwise direction. This is an Amperian loop. Okay, and suppose there is a B, C, D 4 point. Okay, A, B, C, D. So here the total magnetic field here in that Amperian loop. Okay, so next page. So see that okay here. Now see that very carefully. A to B part. Okay, total magnetic field is a B dot ds closed line integral, that is equal to from integral A to B that is B dot, there's a line integral, suppose not the close sign here, that is B dot, that is L, suppose called DL, or DL or DS both are the same. Okay, that is DL, both that's length B, suppose that length be that L. Okay, there's a length BL, so DL both are in same direction, so B in that direction, DL also the same direction. There's a pink color line represent the L direction, and plus B to C, B dot DL same. Suppose we choose as a square, and next C to D, B dot DL plus D to A, B dot DL, and you see that B and DL from A to B both are in same direction. Okay, if both are in same direction, so if there is a cos 0 be the 1. So B, A to B, that's DL. Okay, and here B to C, L is upward, B in that direction. So angle with the 90 degree, cos 90 with the 0, plus D dot B dot DL at C to D point outside. Outside the solenoid there is a no magnetic field. Okay, so that's why B is 0. Now A to, sorry, here is a D to A. Sorry. Here is a D to A. D to A, that's L in that direction and B in that direction. So there is angle 90 degree. So 90 degree cos 90 with a 0. That's angle with a 0. So finally we get B dot ds, that is equal to B integration dl with the L. Finally get L. Okay. And here is the L is very important. Okay. So here find that is a number of turn per unit length. So choose the N is a number of turn per unit length. Per unit length. That is okay. So here with another term introduced here, N, number of turn with the N, and there is a length, we say that the length is L. Okay, and that is equal to, from Ampere's law you know that mu 0 I n close. Another term is that the N, number of turns. Okay, so here finally we get BL. Here the N and the turn per unit length, that is N equal to mu 0, capital N replaced by small n times L. I n close, LL cancel. So finally get B equal to mu 0 N I n close. That's the final expression of magnetic field. Okay, that's very important for solenoid. Okay, that's a very important question for board exam. Derivation of B equal to mu 0 I n close. That's very important. Okay. Next we discuss the toroid. Toroid, there's a solenoid, the toroid. Toroid is look like a, a donut shape. Okay, look like a donut shape or ring, like, okay, there is a donut shape. Okay. Uh, and suppose there is a dot, dot, here is a cross, here is a dot, here is a cross, dot, cross, dot, cross, here is a dot, cross, dot, cross, dot, cross, dot, cross. Okay. Now the dot, so magnetic field in that direction, current in that direction, I. So that is the current I in that direction. Now the green color represents the current I. So if I apply the right hand thumb rule here, so magnetic field, if I choose the Amperian loop, actually if I choose here the Amperian loop is inside a donut. These are the Amperian loop. Okay, so here the magnetic field in that direction, B, B, that's the clockwise direction. Okay, if I apply right hand thumb rule, current, so that is the inside. Okay, that's the inside direction, that is the clockwise direction of magnetic field. And here is an Amperian loop. Choose, and these are the Amperian loop here. Amperian loop, and there is a hollow gap. Okay, there's a gap, hollow or empty. Okay, remember that. Now there is a point, and Amperian loop. The radius of the Amperian loop is the r, small r. Okay, so apply that Ampere's law here. When Amperian loop, there is Ampere's law. So Ampere's law equal to B dot ds. So finally get B here, ds, integration B and ds. Ds means the circumference of the Amperian loop, that is a 2 pi small r, that is equal to mu naught I enclosed times capital N, number of the turns. Okay, so finally we get B equal to mu 0 I enclosed number of turn by 2 pi r. That's the magnetic field inside the toroid. Outside, suppose here is a zero magnetic field. Okay, that's important. Outside there is a zero magnetic field. Okay, outside approach point here is a B equal to 0. That's the toroid. Clear? Actually, that's the line is dot 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 to cover these all these donut. Okay, there is a spring actually. There is a spring actually. Drawing is not good. Actually, behind that it look like that dot 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 back like this. This is the back, and similar concept is the back here, and this back dot dot. Okay, that is dot dot dot. Okay, now cross, and this line comes from here. Current direction in that direction. Okay, there's a two basic concept here, what is solenoid and what is toroid. Okay, that's a complete lecture here. If any doubt what is a solenoid and what is a toroid and how to apply the Ampere's law here, and you ask in comment section, I will try to give the answer. So next class we discuss a new concept and new topic. Okay, thank you.